Hello, people.
Who said that? Is that Tyler?
Nah, it was me, Yusuf. You always say
Well, thank you. Thank you. I don't have to say it now.
that.
Okay. What do we got?
Donald,
Hello.
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 Can I speak with you after class?
Sure.
Okay.
Let
Thank
me
you.
send you a separate Zoom because this one's being recorded.
Okay, no problem.
That's Vanessa, right?
Yeah.
Okay. Okay. Can we see your faces real quick? I'm just waiting for a couple more people to show up. There's Vanessa. There's Sabor. Elijah. Michelle Simpson. Angelique. Cold in your apartment, Angelique?
Yeah, it's freezing.
Yeah, mine too. My wife keeps it at 58. 58. I can afford more. I know I can. Oh well. Zach, don't get married. Stefan McCain has come. Sammy Robinson is here. There he is. Hey, Sam.
Well,
Feels like a class when we can see each other, doesn't it? Victoria, I haven't teased you in weeks. Let's see. What's that hanging on your wall back there?
There's shelves over there and then pictures behind me.
Oh, okay. All right. Well, I guess this isn't what we came here for, right? We came here to do some learning. Let's get the learning started. So I just uploaded the, I'm changing this, the way I presented this chapter last year, I'm changing quite a bit. And I just uploaded the PowerPoint like 5-10 minutes ago and the new notes. If you go through this chapter, hopefully you guys are reading this book too. If you go through this chapter, I find it a little annoying the way they put things together. It makes sense from kind of an experimental point of view, but it really breaks the story up. The way they do it is they go through like, how does the primitive streak get started in chick? How does it get started in mouse? How does gastrulation happen in chick? How does it happen in mouse? How does neurulation happen in chick? How does it happen in mouse? And when I did this last year, everyone was like, is this chick or mouse? What the hell's going on? Where the hell am I? So I think to make it a little more clear this year, what I'm going to do is all chick, which is, here, here, and here in the chapter. And then I'm going to do all mouse after that. We'll see. We may even have an exam after chick. We'll see how much we get through. Last year, I had 2 exams for this chapter. It's a big chapter with a lot of good stuff in it. We'll see how far we get before our next exam. If we get through it all, we can have the whole exam on this, and that last quarter, we'll just have like ice cream socials, you know. It's funny when I was in high school, I took Spanish. Let's see, what was it? Like 9th, 10th, and 11th grade. 3 years we had Spanish. The Spanish teacher was horrible. I don't think he could speak Spanish. And time we were juniors, about all we did was have ice cream socials every day. As a result, I still cannot speak Spanish. Okay. Although it was good ice cream. Let's get started. My PowerPoint. So this first slide of the PowerPoint is just kind of BS, really. I think what I was trying to show is what we're going to be talking about later in the chapter is Hox genes and how different Hox genes are important for different parts as you go down the arm. Not that important right now. So here we go into Hox genes again. It's going to be weeks before we get to Hox genes. Again, this is the way they start the chapter, but then they don't talk about it till later. So don't worry about that now. And then also neural crest cells, which will be important later in the chapter. So once we get when we start doing neurulation, we'll see how these Hox genes come on during neurulation, so that, you know, that AP axis, then like if you take a somite out of here, it already knows where it belongs, because as it's being laid down, you get different Hox genes turned on, and that gives you the patterning. So that's a really cool thing, and we'll see it later, but it's not important now. And then, oops, once you have neurulated and you've got a spine, then you're going to have these migratory neural crest cells starting to move around in order to make other parts of the nervous system. So we'll get to that eventually. I know you're on the edge of your seat now that I brought it up, but be calm, people. We'll get there. Okay, so what we are going to talk about today is the formation of Kohler's streak. If you remember from chapter 3, that's, excuse me, the beginning of gastrulation in the chick is when Kohler's streak forms on this posterior side of the embryo. So the first question we want to talk about is how, hang on a second, let me look at my notes real quick just to make sure I'm not getting ahead of myself. Okay, quick review of gastrulation in the chick. So first, remember you've got your area pellucida, which is pellucid, or you can see through it because there's only one layer of cells across the top, and that's the blastodisc. And that's the actual embryo proper. And then around it, we've got epiblast cells that will then, is it epiblast? No, that's not right. It is hypoblast cells that form the margin and then grow over the yolk. So you've got this, and then between those hypoblast cells, under the blast, hypoblast, between that and the blastodisc on top, you've got that subgerminal space. Sub meaning under, germinal being your epiblast again. So Kohler's sickle forms at the posterior side, and then the primitive streak goes forward from there towards the anterior side. So here is our area pellucida where it's thin, and then these are your hypoblast cells growing across the yolk. This yellow part on the bottom is the yolk. And you've got thickened areas at the side, which is just cells built up, and that's the area opaca. This is where we're going to get our Kohler sickle forming. Okay, here we are almost about ready to start gastrulating. Here's subgerminal space I was talking about, and these hypoblast cells all across the bottom. And we'll see shortly how these hypoblast cells are really important for determining the primitive streak and following it as it's moving along there. And we'll have other cells coming up over here that are endoblast cells, and they'll be important too. Okay, so that's just kind of the brief overview from chapter 3. So chapter 5, Kohler's sickle. So how does this Kohler's sickle form? It's really hard to figure stuff out in chick, because all the way up until gastrulation is about to start is inside the chicken, and you can't just keep killing all your chickens to take the eggs out and find out what's going on. So it's really hard experimentally to get at this. But what's happening here is this egg, as it's coming down the oviduct, it's turning pretty fast too. Imagine this, it's going like one full rotation every 6 minutes. So it's turning quite quickly as it's coming down. And it takes about a day to lay an egg, right? A chicken will lay 6 eggs a week and take a day off. So anyway, this thing is rotating, and as it's rotating, the yolk moves, but the blastoderm doesn't. It just kind of like, it settles at a 45-degree angle here, and then the yolk is moving with respect to it. So something about this is causing this area here to become Kohler's sickle. Okay. I can blow that up. Come on. Okay. Okay, so again, here's your blastoderm or your blastodisc here, everything's spinning in this direction. So all this yolk is kind of coming across the blastodisc in this way because it's affected by gravity, but this is being held in place by something, probably the chorion or something. Okay. Okay, so location, what the hell? I've got this, okay. So here is where your Kohler sickle is going to start, and there's your Kohler sickle there, and the primitive streak going up. So your Kohler sickle is basically the same as a Newcomb center in Xenopus. It's not the node, right? So it's not like the Spearman. It's like the Newcomb center in that it induces the changes to happen in other cells. And what's going to happen here is just back up again. So this marginal zone, so the marginal zone is between the area opaca and the area pellucida. All these cells here in the marginal zone here, all the way around the embryo, they're producing Wnt. So Wnt's being released everywhere around here. And over here is where our Kohler sickle is now. And our Kohler sickle cells are Kohler's sickle cells are producing Wnt. So, I'm sorry, producing VEG1. So VEG1 is a TGF-beta-like signaling molecule, as we all know. I remember we said it was really important in Xenopus, although we never really talked about what it did. It didn't really come up much, but just know that it was there. But here it's really important in chick. It does with VEG1. If you have some embryos and you block VEG1 by maybe injecting a dominant negative or something, you don't get any access at all. So back in the Xenopus days, if we had blocked one of the nodals, one of the X-Wints, that would be okay because you got other ones. There was a lot of redundancy in that mechanism. Here you have to have VEG1 or else it won't form. And also you could take some cells like fibroblast cells, which are just kind of generic cells that are kept in culture a lot. And you could put a gene for VEG1 in it and have them produce VEG1 and take those fibroblast cells, which have absolutely nothing to do with an embryo, put them over here. And just because they have VEG1 in them, they'll make another axis over there. So VEG1 is really important. VEG1 and Wnt, but Wnt is everywhere around that epiblast. So it's always going to be there. Okay. So what else did I want to say about VEG1? Just consulting my notes so I don't lose myself. Also, VEG1 is going to inhibit another primitive streak from being induced. So once this gets started and gets going a little ways, it's going to start putting out a diffusible factor that inhibits another primitive streak from forming. So that little experiment we did where you put your fibroblast cells over here only works up to a certain point. And after you get a primitive streak starting over here, then you can't get another one over here because it'll produces these inhibiting factors that diffuse away and inhibit that second streak from forming. Okay, so VEG1 is really, really important. Wnt as well. So VEG1 is activating SMADs. I'm not sure which receptor SMADs, but definitely SMAD4 because that one gets activated all the time. And then Wnt's are activating beta. So we've got those transcription factors together working on these cells. And what happens is that induces those cells to become nodal releasing cells. So nodal, again, XNR, but here in chick, we just call it nodal. So nodal, these cells here, because of that VEG1 and the Wnt are now producing nodals. Nodals, along with FGF, we'll see in a second, are going to cause the epiblast cells to actually start to move and ingress. So this is like the beginning of the primitive streak formation. But we're going to limit it because we've got these hypoblast cells all across here. And these hypoblast cells are secreting Cerberus. So Cerberus then, if you remember, blocks both Wnt signals and TGF beta like signals. Before it was the X nodals, the Xenopus nodals or BMP4. Here it's VEG1 that's being inhibited. So Cerberus then is blocking this from going any further. So these cells alone are going to start becoming that primitive streak. So here is this other player coming into play here, the prospective endoblast cells. So this hypoblast, if we didn't have endoblast cells, this hypoblast would totally block that primitive streak and it would never go anywhere. But these endoblast cells are going to start to divide now, and they're pushing this way. And as they push that way, they're displacing these hypoblast cells further towards the anterior side of the embryo. So I'm not crazy about this figure, but you ought to imagine in the last figure, the hypoblasts were green. Imagine that now the green starts here and goes that way. So these are no longer hypoblast cells, they're now endoblast cells. And endoblast cells don't release anything as far as I know, definitely not Cerberus. So that's going to allow this primitive streak to start to move to the anterior side. As we're pushing the blocker away, it's going to follow and head up that way. So what actually is the primitive streak? The primitive streak, that endoblast here is just a single layer of cells, right? So as cells start to go in, they make a ripple or a fold in that endoblast cell. And that's what the primitive streak is. It's cells moving in and ingressing and giving you the layers that you need to make an embryo. So there's two things that are causing that. One is the nodals. So this is kind of like a self-generating thing, right? These cells produce nodals, and the nodals cause movement here. And also FGF, which is coming from the Kohler sickle over here. So you've got nodals, which again are activating SMADs, and then you've got FGF, which is activating the MAP kinase pathway. So two different pathways being activated here, and that's causing these cells to start to move. So here you can see the epiblast cells are proliferating, and that's causing more cells. And once they get over to here, they're diving in and going this way. So again, primitive streak, you've got this flat thing of epiblast cells, and these cells start to go in and curl under and move into, and always anterior and lateral to where they're going in. Keep that in mind. It's always anterior and lateral as they come through. We'll see that with the mouse too when we get into mouse gastrulation. So mesenchyme, there's a word I've used before. Hopefully you know what that means. Mesenchyme is kind of a generic term for cells that are not kind of stuck together anymore. They're kind of individualistic, and they're moving on their own, and they're crawling in. So, and again, as opposed to our Xenopus, where you had that, you had at the blastopore lip comes in as a sheet of cells, and that whole sheet of cells moves along. Here we've got cells dividing, being induced by FGF and VEG1 and nodals, and then crawling in, and they're going to crawl across here. So they're not just kind of like floating around stupidly in the subgerminal space. They crawl in and anterior and lateral, and then they cover that part of the embryo. And once the primitive streak gets all the way to the other end, you get Henson's node. So that's going to be analogous to the Spemann organizer when we get that. We're not going to talk about that till the next class probably. So let's go over this again. This is I think it's kind of complicated. I think it's really neat though, because it totally makes sense out of everything. So the beginning is you've got the egg coming down the oviduct, and it's rotating as it goes down. It's going heavy, the thick part first too, by the way. I don't know if you knew that, but it's leading in this direction. So as it's coming down, it's rotating, and that's causing this blastoderm to kind of lean over to the side. So your Kohler sickle will appear here at the top of that, and that will be the posterior part of the embryo. And again, they say they don't know if it's because of different factors in the yolk that are running into the blastoderm at different times, and that's doing it, or if there's some kind of mechanical thing, like the cortical rotation we saw in Xenobus that's causing it to rotate and then that to be posterior. It's not really well determined at this point, but that's where your Kohler sickle is going to be. And it is a Kohler sickle because it's going to have a lot of Wnt, but everything around that marginal edge has Wnt, but VEG1 is being produced here. And that's what's making this the Kohler sickle. So these cells are inducing these cells to make VEG1, and that's going to affect the next door neighbor cells. All over the yolk here, you've got this hypoblast cells. And these hypoblast cells are going to block that primitive streak from coming. So you've got VEG1 and Wnt here, turning these into nodal producing cells, and nodals start to be released. Then we're going to get FGF being released here from Kohler's sickle. And those two together start that primitive streak moving forward. Or it starts the cells to come in and ingress. What makes the primitive streak move forward then is when the endoblast cells start pushing the hypoblasts out of the way, and then that blocks that inhibiting Cerberus signal that was stopping the thing from moving. So this hypoblast moves out of the way. That allows this to move forward, and it's moving forward because cells are coming from the side in and up like that. And always kind of anterior and lateral. So that's the beginning of gastrulation. Any questions about that? I may have gone over it a little bit fast. It's always easier in class because I can see the startled looks on your faces, but oops, shoot, that's a startling move. Damn it. Where the hell was I? Okay, so at this point in the lecture, if not in the development, we've gotten to here. Okay, gastrulation has finished. So once gastrulation is over, pretty much this embryo is patterned, or it's faded anyway. Everything's faded at this point. I want to kind of digress for a moment and define some terms. I've been using these terms, all semester, and I don't know if I ever defined them in the first place. So let's define this. So saying that cells are faded means that if you leave them in the embryo as is, they will become this, okay? So this is faded to become neuroectoderm. Now that doesn't mean it is neuroectoderm. At this stage, at the end of gastrulation, if you took these cells out, they would still just be epidermal ectoderm. But they're faded to be that because of their position and what's going to happen in the future. So that's one thing, faded. Another thing is induced. So induced means that a hormone has hit cells and turned on their transcription factors, okay? And that is inducing that cell to change cell fate. And then the third thing, third word I wanted to define is specified. So specified means now it is that thing, okay? So once it's induced, it's specified, which means at that point you could take it out of the embryo and it would be that thing. So keep those three words in mind: faded, induced, and specified. They're all different and they all mean different things. If you want me to, I can write that down in the notes somewhere. Just let me know afterward with an email or something. Okay, so after gastrulation is done, okay, this is all going to be neuroectoderm, and notice it's anterior to Henson's node. That's important. We'll see that in the next class. And then the primitive streak is still here. Here is mesoderm. That's going to be somites and lateral plate. And then down here is extra embryonic mesoderm. So that's going to be, some of the structures that attach the embryo to the shell and all of that kind of stuff. And then, of course, on the outside is the epidermis, fated to be epidermis, and that will grow over everything. So the chick will not be born without skin. That would kind of suck. Unless you like boneless, skinless chickens, you could develop something like that, I imagine. You know, what's funny? Years ago, someone said to me, an undergrad student at a meeting of, I think it was a Sigma Xi meeting, said, you know, they changed the name from Kentucky Fried Chicken to KFC because now they're growing their chicken in test tubes and it's not really chicken. And legally they had to change the name. No, it's just so much easier to grow a chicken than to do it in the lab. I mean, you ignore chickens and they make more, right? That's what chickens do. Okay. All right, so here we are showing where the fate map stuff is coming from. So here at the posterior side, you've got your extra embryonic tissue, and then this early part of the primitive streak is going to be more ventral. So here's heart mesoderm, lateral plate mesoderm, and then kidney mesoderm. And as you go further forward, now this is middle mesoderm, more or less. Like whenever you hear somite, that's your spine. So that's both axial, meaning in the center, and further up than like the tail and the extra embryonic stuff. And then up here, you've got medial part of a somite. So here's Henson's node. We haven't got a head yet. The whole head is going to be forward of Henson's node. So it forms up here. And again, the reason why I can do that is because things go in, through, and forward. So the node doesn't have to go all the way up here to induce the head. It just lets those cells come through. It induces them as they're going through, and then they crawl forward and they form those structures. So that's a really neat process that we'll see probably in the next lecture. But here again, in the anterior end, you've got your axial mesoderm, which is nodal cord, axial meaning central, nodal cord and Henson's node. Paraaxial mesoderm, which is on either side of the axial mesoderm, and that's your somites. Ahead of this, you end up with your head and brain type stuff. As you go further posterior, you get intermediate mesoderm, kidneys, reproductive organs. Further back, you've got more ventral stuff, lateral plate and heart, and then you've got extra embryonic mesoderm here. Okay. Questions? Comments? That's about what I wanted to talk about today. I swear to God, it took longer when I practiced it. I know you guys know that story when you give an oral presentation. You practice it out at 17 minutes exactly, and when you say it out loud, it's 5 minutes. Okay, I'm just looking at my notes real quick. All right, yeah, that's about what I got for you today. Wednesday, we will be doing this, which is the neurulation. So that primitive streak goes up, Henson's node forms, and then it comes back down to neurulate. So we'll be doing that in the next class. Okay, any questions, comments? I haven't started grading your exams yet. I'm going to do that as soon as we hang up here. So you should hopefully, what time is it? It's not even, it's still 1:30. I should be able to get them done today. So you'll have your grades up on Moodle probably by 4 o'clock. We'll see. Any questions or comments here? I'm feeling guilty because I'm stopping 20 minutes early, but that's kind of the way we've been going lately.
No, that's fine.
That's fine. Okay.
Perfect.
Okay. All right. Well, I guess it's been lovely. Vanessa, I'll send you a link right now, and I hope to see you all again here on Wednesday. Bye.
Bye.